do is just plug in the derivative, a number to the left of -2, like let's say -4. A number between -2 and 0, like let's say -1. Then there is no need, they have to be the same, but let's do it because it's even, right? Oh, what? Oh, I'm sorry. Yes, that's correct. But I'm looking at the derivative. That's correct. And then let's say 5. So the signs are negative, positive, negative, positive. Negative, positive, negative, positive. Good. So we studied the sign and we put it in the table. At this point, number 8, identify max min. Okay, so let's identify max min. At this point, this is when I catch my mistakes. If these two rows do not work perfectly in sync, they're not in sync, they don't work perfectly, then I know, oops, something is terribly wrong. This is when we find out. Let's see. From infinity to 0, yes, that's correct. From 0 to -5, yes, that's correct. From -5 to 0, yes, that's correct. From 0 to 3, yes, that's correct. From 3 to 0, yes, that's correct. From 0 to -5, yes, that's correct. And from -5 to 0, yes, that's correct. And from 0 to infinity, that's correct. So in my list, I identify the max min and the same time increasing. I didn't write it yet. Increasing, decreasing intervals. You don't have to write them on the side. It's very clear. The function is decreasing between -infinity and -2, union between 0 and 2. The function is increasing between -2, 0, union 2 to infinity. You don't have to write it. I see it here in the table. There is no need to write it again. So now, can anyone tell us -2, -5, what type of point is this? -2, -5. What type of point is it? It's okay if you're wrong. What do you think?
Absolute minimum.
We don't know absolute or not, but it's definitely a relative min. Very good. Look at the sign. Change. Good. 0, 3. 0, 3. Relative max. It could be an absolute. We will see that at the end, but not right now. Good. Awesome. What about 2, -5? 2, -5. Anyone? No one has any idea what type of point is 2?
Another local minimum?
Yes. Local or relative minimum. Awesome. So at this point, we finished everything about the derivative. We have critical numbers. We determine the function values at those points. We put them in the table. We study the sign of the derivative. We identify the max min. We also identify the increasing, decreasing intervals. Now we are looking at the second derivative. Number 10, the second derivative. Okay, so here is the first derivative. The second derivative will be 6x² - 8. Like before, we have never discussed the second derivative. Now we're doing it. Now we're discussing the second derivative. Like with the first derivative, the second derivative could be 0 or undefined. Not for this function. And what we get from here, 6x² - 8 = 0. 6x squared equals 8. X squared equals 8 divided by 6 divided by 2, which means 4/3. And then we take the square root. Remember, you have to get a plus and a minus. So it's 2 divided by the square root of 3, but I have to approximate them. I don't know where to put them in. Okay, so I will approximate. If I find my calculator, it's right here under my papers. So 2 divided by the square root of 3, 1.2. So plus or minus 1.2. Of course, I had to get a plus or minus 1.2, so it gets even crowder here. 1.2, 0 for the second derivative, negative 1.2, 0 for the second derivative. I immediately have to determine the function value. So with our list, so second derivative, the second derivative is 0 or undefined, 12. If we get solutions from this, then I have to find f of those numbers. So let's say solutions. So I'll say solutions here. You saw what I did? We determined, if you want to say critical numbers for the first derivative, but let's not go there. So we said the second derivative equal to 0. We found some solutions, and now I have to plug them in. So the two solutions are negative 1.2 and 1.2. And of course, these numbers have to be the same because the function is even. But I have to plug it in. So in the function, in y equals, now I will put the function. Who knows where the original function was? 10 pages ago. Okay, I'm going to put it in. So 0.5 x to the 4th. And then minus 4x squared. And then plus 3. Okay, so I only want for the function, which is in red, and I only want negative 1.2. And if you try 1.2, you have to get the same answer. Negative 1.72. Negative 1.7 is good enough. So negative 1.7, negative 1.7. Okay. Now, what these 2 points represent, negative 1/2, negative 1.7, 1/2, negative 1.7. So number 13 on the list, study the sign of the second derivative now. That's easy because 6x squared minus 8, when I plug in negative 10, this will be a positive number. When I plug in 0, this will be a negative number. And when I plug in 10, will be a positive number again. Now let's analyze what this means. Okay. So at this point, we found 2 points, negative 1.2, negative 1.7, and 1.2, negative 1.7. These points are called inflection points. When the second derivative is 0 or undefined, of course the function has to be defined. And super important, f prime of x, like with the first derivative, changes sign. So I did not show an inflection point. I will in a moment. As you see at this point, the second derivative is 0 at negative and positive 1.2. And as you see, it changes sign. That's why this point is an IP. This point is an IP. Inflection point, inflection point. Relative min, inflection point. Relative max, inflection point, relative min. Okay, let's discuss what that means. when we say inflection point. So I can write it here. No, I want a graph here. So I'm going to write it on page 15. IP, or inflection point, is when a function changes concavity. Changes concavity from opening down to opening up, or from opening down to opening up, or from opening down, opening up to opening down, from down to up, or from up to down. In other words, we like to say it holds water, it does not hold water. This is the IP at that particular point where the function changes concavity. Opening downward, opening upward. Downward, upward. I'll put my sign in here, like I did with the arrows. Holds water, does not. Holds water, does not. Now I see the table is complete. We study the sign of the second derivative. We establish the inflection point, or points, and concavity. When it opens up and when it opens down. You don't have to separate and write it down. It's very clear to me. You put the symbol. I know that between negative infinity and negative 2, union between 2 and infinity, the function opens up. And between, no, I meant negative 1.2. So negative infinity to negative 1.2, it opens up. Union 1.2 to infinity, opening up. Between negative 1.2 and 1.2, the function opens down. This is in the table. You don't have to write anything else. If you fill out the table, I'm happy. Now, this list, what I did with the second derivative, what I did with the first derivative, what I did with the x and y intercepts, don't mean anything anymore. I have all the information in the table. That's all I need. I only need the table to graph. And now we're ready to graph. Do I still have time here? Yes. Yes, I do. Okay, so that's it. We're graphing the function. We do not need any other page, any other calculations, nothing but the table. So we have to take it slowly, step by step. I'm trying to find a piece of paper to cover the rest. Here it is, my notebook. Because I don't want us to look ahead. You will see in a moment why. So you understand every step. First, before I do this, I need to plot all the ordered pairs I have. Negative 2, so it's anywhere between negative 3 and 3. 1, 2, 3. 1, 2, 3. So negative 2.68 comma 0. And the 2.68 comma 0. Negative 2 comma negative 5. Negative 2 comma negative 5. And of course 2 comma negative 5. Negative 1.2, negative 1.7. And 1.2, negative 1.7. 0 comma 3. Negative 0.92, 0. And 0.92, 0. Okay. So let me, where is my list? Maybe I should put it in writing. Plot all points first. So number 15. plot points. Okay, I did. And now at this point, I'm ready to analyze the table, learn from it, and graph. So the graph is coming from infinity. It's decreasing, opening up, decreasing from infinity, decreasing, opening up to the x-intercept. Okay, fine. It's continued to decrease to the point -2, -5, still opening up. So 2, -5. Continues to decrease, still opening up to this relative minimum. Okay, let's see next. Continues to open up, but now it's increasing to this point that is an inflection point. Increasing to the inflection point, still opening up, but increasing. Okay, let's see. Next. Crosses at -9.92, 0, crosses the x-intercept, but it changes concavity. It's no longer holding water. It's opening down because this was an inflection point. So it changes concavity and continues to increase, opening down to this x-intercept. Okay, moving on. It continues to open down, going to the relative max on the y-axis at 0.3. Opening down, increasing to 0.3. Moving on. At this point, I should stop. I should not even look at the rest of the graph, of the table, because I know the function is even. Whatever I have graphed on this side, I have to have a mirror image on this side. You can continue looking, but I'm going to use the fact that the function is even, and I'm going to do just this. It has to have an inflection point. It has to change concavity. It has to come to the minimum. It has to come back, cross the x-axis, mirror image with respect to the y-axis, and continue to infinity. This is the graph of f of x. 1/4 x to the 4th minus 4x squared plus 3. Yes, it took a chunk of time because